Hello, everyone, and welcome to my presentation on Bell's Theorem and Entanglement by me, Shreyas Dillon. So to start, we're just going to go over a general table of contents, kind of our journey, what we'll be going forward. So first, we have the introduction, which is going to be a general introduction into kind of the field of quantum mechanics, and just to kind of get you guys locked in and ready for what's about to happen. And then from there, we're going to start to get more specific into the historical background leading up to Bell's theorem, kind of previously held theories and stuff like that. And then we're going to go into Bell's theorem, how it was derived, and info about it, / its significance. Then we're going to go into loophole closing, which is after the theoretical derivation of Bell's theorem, how it was experimentally proved, and loopholes in it that were experimentally closed. And then we're going to end with the conclusion, which is the takeaways from all this, etc., etc. Introduction. So, introduction to this is quantum mechanics. It's one of the main primary issues, or not issues per se, but where it deviates from classical mechanics is its indeterminacy. In classical mechanics, when you measure something, you can predict it up to kind of like an infinite kind of accuracy. With quantum mechanics, on the other hand, there is not that determinacy where you can, pretty self-explanatory, you can determine the outcome of something. Quantum mechanics has indeterminacy. Instead, it's probabilistic. So instead of being able to tell exactly where something is, you have the probability of where something is. So as you can see from the picture on the left, this is kind of the mathematical formulation behind it, and this is a good visual. This is an example of a probability density function of a random kind of particle or something we can say. And it gives an example. The probability it's between these hypothetical x coordinates, 4 to 6, is 0.93 or 93%. But the important thing to remember is before actually measuring it, you still don't know where it is. You only have the weighted of, oh, it could be here with this probability and it could be here with this probability. And this feature of quantum mechanics is something many, many physicists found troubling and puzzling. One such physicist being Einstein, where he and two colleagues, Podolsky and Rosen, formed the EPR group and published a paper where they kind of posited that quantum mechanics, as it was not a complete description of a particle or what was happening. Instead, they believed that something was missing, that something was a hidden variable. A hidden variable is exactly what it sounds like. It was some variable that every single particle or something had that determined its state before measurement. So if it was true, then when you measured something, this hidden variable comes into play and gives you the actual value. So the particle before measurement has a value all the time encoded in this hidden variable, and it's only when measured that it comes out. And this seemed to clear up all the indeterminacy, but it was soon after this that our main man, John Stuart Bell, disproved this with his Bell's theorem / Bell's inequality by utilizing entanglement, a very quantum phenomenon that is really interesting. Now for the historical background. This is where we're going to go a little bit more in depth into the EPR group's formulation of their claim for hidden variables. So in this kind of very generalized experiment of what they did, they had an initial source that produced two different particles, one going this direction of particle A going left, one going this direction of particle B going right. And then there was both on either side, equidistant, there were detectors that detected these particles. And what they said, some prerequisites before saying this, that measuring particle A, the one to the left, is dependent on the detector angle. This is basically just saying that these detectors could be put at different angles before conducting the experiment, and these different angles affected how many times they were actually measured. So a measuring particle A is dependent on the detector angle A. These arrows, just there's a lot of them here, is known, it's a vector, because think of it as like this angle, say it's here, then the vector is just going to be there. So measuring particle A is dependent upon the detector angle, and the EPR groups, what they posited, this hidden variable, something that we, or not we, but that quantum physicists prior to that hadn't really thought of, but they are now seeing if it's viable. So it's denoted as lambda here, but just know that this is that hidden variable. And similarly, particle B is dependent on B's detector angle and lambda. The expectation value of the products of both components, a lot of math jargon there, but it's pretty much just the weighted mean of the products of both of these is equal to this. So the expectation value for the products of both of these are equal to the integral of the probability distribution, that's what P of lambda is, times both of these events. The A in all this is basically just saying this event A, which is dependent upon the detector angle and the hidden variables, which both change. Now for Bell's theorem. So the important details to notice that make these two differ slightly is instead of doing what the EPR group did, which I didn't mention before, they utilized squeeze states. So basically what this is doing is in quantum mechanics, as I mentioned before, that kind of indeterminacy, there's also like an uncertainty attached to quantum mechanics. So you're uncertain, and you can only really, if you try and zoom really in to try and predict one aspect of a particle or something, then a different other aspect becomes super, super vague, and you have a very wide range of what that could be. So think of this uncertainty as you try and zoom in too far on this, another thing becomes really impossible to determine. So squeeze states is doing exactly that. They are zooming really in to get a really precise, accurate measurement of one variable of a particle, and then this creates a squeeze state. You're squeezing this uncertainty, you're kind of molding it to be uncertain in the way you want instead of what it naturally is. So by squeezing the uncertainty of the two separate particles, the one going A and the one going B, they entangled them, which means they are linked in a way that means you gain information about one by measuring the other. So instead of using these squeeze states, what we are going to be using is the singlet states for spin 1/2 particles. That sounds pretty complicated, but just think of it as uh, a quality intrinsic to particles is spin, the kind of intrinsic angular momentum, and spin 1/2 means they both have spin 1/2s. It just can be spin up or spin down. And what we're going to be doing, which is convention, to take away some of the unnecessary variables, if it's spin up, it's going to be +1. If it's spin down, it's -1. And these kind of singlet states just make it the kind of maximally entangled states or Bell states. So it makes it the entanglement and the contradictions that we're going to see soon a lot more evident. And then another difference is that instead of the detectors being perfectly aligned and kind of set as they were in the EPR groups, these detector angles differ from each other and they can be rotated independently. And just a little something to get you into before we get into the actual math, the expectation value for this probability of A, B, so the probability of a measurement based on A and B, is going to be -A times B. So remember, these vectors just represent the angle of the detector. So you have negative the angle of A times B. And now we're going to get into the derivation of the actual theorem. Sorry about that. Try and bear with me here. So we found before that the probability or the expectation value is, again, just think of that as the weighted average based on the probabilities. Remember, we talked about that, how different things have different probabilities, is going to be this. So the integral of the probability distribution of this hidden variable times both the outcome of A and the outcome of B. So as we mentioned before, the detectors were aligned in the EPR group, which means they are anti-parallel results. Because they're exactly aligned, we know that the results will be the same because the detector outcome or the detector angle won't affect them. So this anti-parallel results means that if the first particle comes up spin up or 1, then we know the other one has to be spin down or -1. This is due to the singlet state that we use, these kind of maximally entangled states. that allow us to know information about one particle based on the measurement of another. So with this information of antiparallel results, that if we know one is spin up, then the other has to be spin down, we get that this event A is just equal to negative B. Because say B turns out to be -1, if you -1 is just +1, and you have exactly what we had before. If one is spin up, the other has to be spin down. And then from here, we just get B is equal to -A. So from there, we can change our equation, taking out the B and just inserting -A. So you'll see now there is a negative sign in our integral that we added in there. And additionally, there is this now two A's instead of A and a B based on our based on our deduction right here with the anti-parallel results. And then now this is the part that tricked me up the most when I was deriving this. You introduce C, which is another unit vector. Just think of unit vector A was a measurement of one detector, B was the other, and this C is any other unit vector. So what messed me up the most here is I always try and apply it to the experimental context, like how does this play into the experiment? But for here, it's pretty tough to find an actual application, but from a mathematical standpoint, it's necessary to move on. So here we are introducing C, which is another unit vector, to change our equation from just P of AB. We are adding in P of AB minus P of AC. So this is just the expectation value of the product of the A vector and the C vector. And the only difference this adds into our thing is we have to throw in this extra A of A lambda and A of C lambda. This is exactly what we did up here with just the P of A lambda, no, P of A and then comma B. We just switching in B and or A and C instead of A and B. From here, we have a simplification we can do, or a factorization actually, where we know that this value here, A or outcome A with or not outcome A, this is A with the B vector and lambda. If you square it, it equals 1 because the outcome is plus or minus 1. And if you square that, it's always going to be positive. So it's just 1. And then so here we're going to be factoring out this term, as you can see in this right, A of the A vector lambda times A of the B vector lambda. And if you just multiply it all in, it'll simplify. And then now from here, you're going to take the absolute value of both sides. So taking the absolute value of the left side gives you exactly that. And then this is going to be the right side. And you're going to say, whoa, that is a big difference. There's an inequality, and you're missing the term that you just factored out on the right. And then so here's how that happened. That term on the right is A of A lambda times B of, or A of, yeah, so the expectation value of this product right here. A of A or A of the A vector lambda times B of the B vector and lambda. So we know that both of these individual terms equal plus or minus 1. So when you multiply them, they were also equal plus or minus 1. The absolute value of plus or minus 1 is, you guessed it, 1. So we can just take away that term because we know it has to equal 1. So we're just multiplying by 1. The second term, P of lambda times 1 minus A of B lambda, comma, or A of the B vector, comma, lambda, times A of the C vector, comma, lambda, has to be greater than or equal to 0. Because probability distribution is always greater than 0 because it's probability. And you know that that second term in the brackets has to be equal to plus or minus 1. So the greatest or the lowest this could be equal to is 0. So now we have, because it has to be positive, it doesn't get put into absolute values because the absolute value of a positive number is just that number. And it changes because it's greater than or equal to 0. It's not just a set value. It changes from an equation to an inequality. And then from there, we have produced this step, the bottom step, from the top step. We've changed our equation into an inequality. Now from there, we can distribute out the P of lambda to get the integral of P lambda, also just using integral rules, the integral of P of lambda minus the integral of the second term. And then from here, we have the integral of P lambda equals 1, because the integral of any probability distribution is 1. because the probabilities of something has to equal 100% or 1 has to be somewhere. And then the second term just simplifies to P of B vector comma C vector. And this simplification may seem tricky, but if we go up to what we had before, what we pretty much initially had was the P of A vector comma B vector was negative integral of the distribution times A of A vector times A of B vector. If we scroll down to what we have negative P of lambda times A of B lambda times A of C lambda. So our only differences is instead of A and B, we have B and C. We can change that to just be P of B of C. And then from there now, we have our, ta-da, Bell's inequality. So the absolute value of the left side, which we all had, is going to be less than or equal to 1 plus P of B vector comma C vector. Look at that. We've done it. That was a lot. Feel free to go back and rewatch, look at the steps, because I am speaking pretty fast. But now that is going to be the local hidden variable prediction for that. So that just encompasses all the local hidden variable prediction. Now we have the quantum mechanical prediction for the expectation value. These brackets here represent the expectation value, and this S1 of A times S2 of B represents our two different particles measured at A, which is going to be our A vector, B, our B vector. We can already see just based that this is going to be kind of similar based on just having two different vectors, A and B, and two different particles. And the quantum mechanical prediction for this is negative h bar squared over 4 times cosine theta. The actual derivation of this would take a little longer. We don't have time for that. But continuing with our convention of making spin up 1 and spin down negative 1, spin up in this notation is h bar over 2, and spin down is negative h bar over 2. So changing those to just 1 and negative 1, we just get negative cosine of theta. So now we have what our expectation value is going to be for quantum mechanics with using the hidden variable theories, which is what we just derived, and the quantum mechanical expectation value, which we just found here. We can now choose our detector angles to actually provide a numerical disproving. Because right now we just have Bell's inequality. We don't see why it's actually disproved. So all we need to know now from here is that theta, this angle right here, negative cosine of theta, is going to be equal to the detector angle of A minus the detector angle of B. So now, moving forward from that, we can choose any detector angles we want. So of course, I know the answers, or I guess I don't know the answers, but I chose here the angles of each of the detectors that provide the maximal disprovement of this. This is just going to provide the most glaring disprovement. Just think of it as hypothetically, the detector is just rotated, because remember they can rotate independently and differ, that they were these two. There are many other ways they can differ and contradict. This is just the one that proves the simplest. So you have detector A is at 0 degrees. The vector C, remember the unit vector we introduced in the earlier section, is at 45 degrees, and the detector B is exactly at a right angle, 90 degrees. From here, we can go back to our Bell's theorem, which is right here, and then use our quantum mechanical prediction, negative cosine of theta, to plug in values of now our A vector, B vector, and C vector to actually get a numerical disprovement. So P of A vector, B vector, A is 0 and B is 90. And we know theta is A minus B. So you have, excuse me, negative cosine of 0 minus 90. Cosine of negative 90 is 0. And we're going to follow similar steps for the next two to get P of A vector comma C vector is root 2 over 2, and P of B comma C is, oh no, negative root 2 over 2 and negative root 2 over 2. So we have the absolute value of negative root 2 over 2, which is root 2 over 2 on the left side, is less than or equal to 1 minus root 2 over 2. And from here, it's pretty clear there's a disprovement, or there's something wrong with the equation. But if we take root 2 over 2 to equal 0.707, we have 0.707 is less than or equal to 1 minus 0.707. So, sorry, You have 0.707 is less than or equal to 0.293, which is evidently false. And congrats, we have disproved local hidden variable theories, proved Einstein wrong, and seen Bell's inequality at work. That is enough math for today. Now we are going to go back and go into past theory, now into the experimental loopholes that were closed. This actually recently won a Nobel Prize, which is pretty awesome in my opinion. Shows how important this work was. But let's go through it. So the first experimental proof of this was by J.F. Clauser, who used two detectors that varied independently and a calcium atom that emitted entangled particles, and found that these results and the rates were in line with what Bell had found, and that they disproved hidden variable theory and meant that quantum mechanics was something else entirely, or this effect from quantum mechanics was something else entirely. Now for the first loophole was the locality loophole. This loophole was based around the fact that the detector angles were chosen before the particles were released. So because of relativistic causality, which is, I might be explaining it pretty poorly. Give me 1 second here. Sorry about this. I just want to make sure I don't get this wrong, because that would be pretty embarrassing. You feel me? Okay, so in both of the experiment and in Bell's kind of thought experiment, they supposed that both the other detectors didn't affect the other particles. Okay, that was very wordy. But say the angle of detector B does not affect the outcome of particle A, and then vice versa. So in order to actually have this, you needed to choose the detector angles mid-flight, because if you do it before, then relativistic causality basically says that the effect of something cannot come before its cause. So if you have it before, there's still some way it could affect it. If you choose it mid-flight, the information cannot transmit fast enough, and you have fixed the loophole. So what Alain Aspect and his team did is they had an optical switch on these detectors that they could switch mid-flight, and it would change the detectors mid-flight, thus closing the locality loophole. There is one more loophole, which is the detection loophole. And Anton Zeilinger, he closed both loopholes at once, which led to the final product and the final loophole-free disprovement. And this detection loophole was based on the heralding efficiency of these detectors. That is basically just saying the amount of times that both particles were detected. So when technology was a lot worse, these particles could only be detected a very small portion of the time, skewing our sample and making our data pretty bad. But as technology increased, the heralding efficiency of the technology got a lot better. And with Zeilinger and Aspect's innovations on the experiment, they were able to close both loopholes, thus proving Bell's inequality experimentally and disproving hidden variable theories. So the conclusions we can take away from this is one of the main reasons why Einstein really disliked this kind of phenomenon of the indeterminacy in all this was additionally because entanglement was used in it, and it meant that information was being transmitted faster than light, because you instantaneously knew, if you could think faster than the speed of light, that if you measured one particle spin up, the other had to be spin down. You didn't need to do anything to that particle. You knew it had to be that. And this non-locality, which is kind of faster than light stuff, think locality is stuff happening less than speed of light, non-locality is stuff happening fast than speed of light. What it did is it was very unnerving, and that was one of the main reasons why Einstein did this, to figure out this complete state of the quantum particles, introducing the lambda, the hidden variable, etc. to kind of say, "Oh no, there's no non-locality. There's this hidden variable that explains everything." But no, nature. One of the main takeaways from this is that nature itself is non-local. There are some phenomenon, or not some, pretty much entanglement is very one of the primary ones that make quantum mechanics such a unique field to study. And yeah, that's pretty much it. Thank you. It's a non-local nature and just really makes quantum mechanics such an individual field, in my opinion. Thank you for watching. I appreciate you sticking with all the math. I know that definitely was not easy. And thanks. Bye.